So, and yeah, please ask questions if you're in the room and also if you're on Zoom. And I hope you had some good exercise session today where you could already play a bit with gradient descent and also stochastic gradient descent. So what we're doing today is that we will finish the optimization chapter. So we saw grid search as a very naive algorithm last time. We saw the basic idea of gradient descent. So including like what a gradient actually is. So, and then what we discussed is when we do it on linear models, and then we switch to stochastic gradient descent. And that's really the algorithm that everything is about. And the only difference here is this little n, as we saw last time, right? So here you only have to look only at one data point. So this is the key difference. If you only look at this one point every step, then you have much less work to do to compute this object. Compute this object is the gradient, or in this case, this object is actually called. So, I mean, sometimes we just call this whole thing here. We call it G, and we say that is we say this vector is a stochastic gradient. And why is it called that? It's just because, yeah, if this is a random thing, it depends on the randomness of which data point n you take. So this random object has the correct expectation. In expectation, it is identical to the full gradient. That's why it's called a stochastic gradient. But in every specific instance you sample from this n, you get a very, very different vector. So, and here is what we said, that it's in expectation, it's a true gradient. And that's about where we stopped. So then we saw this on a concrete example of linear model followed by squared loss. That's what we computed last time. So we computed the gradient by hand, and that's also what you have on the exercise sheet and what you are playing today in Python to see how does this compare. When I do this on a real data set, do my linear regression model, use squared loss, and then let's compare full gradient with stochastic gradient. Okay, so maybe to finish the recap, it's good to see this again side by side, what we had, right? So we had gradient descent, and then we had a stochastic gradient descent. So in gradient descent, we were interested to minimize the full function. Sorry for my writing. Is the average of all data points, right? Small n goes from 1 to big N of like 1/2 if you want. And now here comes the crucial part. So the label minus the model. The model is just a linear one. Here is your model, and then squared loss. Model and data. And then we had in stochastic gradient descent, we kind of ignored this thing, and we said we only look at data point n of the model. And yeah, that's the same thing. It's just we don't do the sum. So transpose and squared, really the same thing as we had before. Why am I doing this? Because I want to show you the difference in the gradient, right? So the gradient we also computed. So full gradient. If you remember this competition we did, we said it's forgot the minus. We said it's minus this data matrix transpose times the error vector. And the error vector is collecting these n points or n numbers how wrong is every prediction for one of the endpoints. So this vector here is called the E, the error vector we had last time, remember. All right, so this is the gradient, and this is actually a n vector, so it has n entries, as we said. And then we discussed how expensive is it to compute this thing. Okay, computing the error vector takes me a bit of cost. That takes me one matrix vector multiplication for this here. And then the addition is kind of for free compared to that. So that we said was, we said that the cost was, so again, this is for a linear model. Then the cost was n times d, right, order, to compute one of these gradients. And then, of course, once you have it, you can very cheaply perform the step. So that was what we had. And now you can ask, so how much cheaper is it actually now that we do stochastic gradient descent in this particular setting? So for that, we again need to do the work, the math, to figure out what is the gradient now just with respect to Ln. And that, of course, this one will only depend on one of our data points. It will not be influenced by the other data points. Because here, what this does here is that it takes the inner product of this E vector, which has like n entries, right? And it sums up all these n errors. So that's why, so this is just another way to write this sum. That's what's happening in this inner product here. So now we don't have a sum. And you can do the compute, and it's really the same computation as we compute the gradient of this thing, because it is just the inner part here. And you will see that the gradient just of this Ln is simpler. It just depends on the nth data point and on the nth error. So that's the answer. And what is this, right? So this is a number. It's just how wrong is the nth data point classified. And what's this here? So this is a vector. And there's some convention. Some people want the gradient to be a column vector, some want it to be a row vector. So, but the crucial thing is it's a vector. So maybe let me use the transpose to be consistent here. So now this is the gradient here. So it's a vector times a number, and it's kind of nice. It's kind of interesting, right? This gradient here it's just the data itself, right? It's just the one data point here, and that with a strange kind of scaling to make it shorter or longer. The scaling depends on how wrong you are currently misclassified as this data point, or how much your error is if you do regression. So this is what this gradient is. It's a very interesting structure. So this also has implications in privacy of gradient descent. For example, you see, we don't share our data. We only share gradients when we train together. That's what, for example, federated learning does in your phone. To save privacy, you can exchange your gradients and train together. So you form a mini batch together. What I'm saying here is that that's actually a bit risky, because you see your gradient is identical to the data, kind of, right? Because the direction is purely given by the data. And then it's just like the length of the vector is given by something else. So here you see that the gradient does reveal some information about the data. So it doesn't matter for us so much today. Here we care about efficiency, but if you care about privacy, that's an interesting observation. So here we care about efficiency. And now, yeah, how expensive is this? So compute the loss for one data point. That's here. Do the gradient computation, which is just this number times the vector. So it's much cheaper than before. Before it was matrix vector, now it's vector only. and the size of this vector is a D vector. I mean, there's two vector operations happening, right? One is here to compute the model, the prediction, that's X times W. That also has cost D, and once you have it, and then you multiply it with your vector, which is the second thing, which also costs D. In summary, this SGD is n times cheaper than gradient for the scalar linear models. And actually, it's actually even easier in the general case, right? Because even if you know nothing about how do you compute gradients of your model, even then, everyone computes the gradient of the sum here by just computing the gradients of the predictions inside. So that's the only way people can compute the full gradient. So it's always that this guy is n times more expensive than this, because you compute it by computing n of those. So that's true in deep learning as well. So even if you just have a black box which gives you a gradient of this, then you call this black box n times, and then you get the full gradient. So that's how you would do it in deep learning. So both in deep learning and in linear models, SGD is n times cheaper than full gradient. And this is assuming batch size 1. So if you have larger batch size, it costs a bit more again. Any questions on this? Then. Okay, there was a lot of competitions here. So now we will switch gears a bit. We go back to general optimization because it's kind of useful for many things. So I mean, optimization is of course also useful outside machine learning, and one thing that can surely happen quite often is if you have a function which is not differentiable. So what do we do then? So we're just minimizing. It's always the same. Optimization is just minimizing a function, L of W. Now, what if this L does not have a gradient, does not have a derivative at the point where you are? Then do you have a problem or not? So that's the question in non-smooth or non-differentiable optimization. Let's look at a quick example. So that's really the most natural toy example is maybe this, and yeah, let me put the error, the E for my variable here. It doesn't really matter, but when you have the absolute value, so that's of course an important function, and it's differentiable if you ask here or here, it's fine, but here at 0 it's not okay. So there is a special point at 0 where we do not have a derivative. So what do we do then? So this is just a absolute value function. Okay, and what we're doing, we're trying to find a thing which behaves a bit like a gradient, but also works when we do not have a gradient. And what should be that thing, that vector? So what properties do gradients have that makes us like them or use them for optimization purpose? So one really nice property that they have is that they can use as a surrogate model. They kind of give us a simplified model to our function. So when we are here at the point W and we were trying to minimize our function, so then maybe that's a hard task, right? The red function is complicated. It's hard to optimize it. So what I do is instead I use a surrogate function, which is a model of my full function, and that model is just linear. So it's just much easier. So what if we do that? So that's what gradients do, like a gradient step. What that means is actually you just pretend that your red function is actually a linear one, right? Because if it's a linear one, then the gradient will precisely bring you down, or negative gradient will precisely help you to, it would be the perfect step to do if your function were truly linear. So it's a good model, but it's in a neighborhood. It's certainly a good model. If you go further away, its model is maybe not so perfect anymore. And so that's why gradients are good. And to make this a bit more precise is that actually you can show that this gradients give you a very nice characterization of what it means to be convex. So and that's, so it's an equivalence here that if you have gradients, then this is an equivalence. So here it means you have gradients. And what it says is that if your function is always above its linearization, so this is the linearization, right? We are at W, and we take the gradient here to do our linear approximation, and then it's the first order approximation. So right, this first order approximation of my function, that's my green model. And if my true function, the red one, is always above it, then what that means is that the function is convex. So this is just an alternative way to say, well, what is convex? And now the way we're going to use this is we ask, can we do a similar thing if our function is not differentiable? Can we have a similar property that we have these nice linear approximations? And that's what a subgradient is. So it's really the same idea. You just ask, does there exist a green function? And this, sorry, does there exist such a vector G such that your model is above the linearization defined by this G vector? So this is something you can ask, right? So here the gradient took this role, and here you just ask, is there a G, any vector, which does the same thing? So, and it's always hard to draw. Okay, maybe I give up. So this is a convex function, the one I just draw here. And it's also differentiable in most places, but not all of them. So you can see when you're here at W, then you have a problem. There is no gradient here. So I mean, if you're here, then things are okay. So here there is only one linearization to your function, and this is given by the gradient at that point. But if you're here, it looks different. So then here there are actually several ways to achieve this property that we talked about. There's many linearizations which all go through this point. So these vectors G, and all of them have this property that the true function will, or the red function will always lie above these green models. So again, green models defined the same way as a first order approximation. Just say the value you currently have plus the linear approximation. So if there exists such a G that the F is always above, sorry, L is always above, then we say this G is a subgradient at where we currently are. Does that make sense? Yeah. So I'm not saying this exists for every function, right? But for many nice functions, yes, you can do that, and it exists. For example, for all convex functions, you can always find such subgradients, right? The red is a convex function, but it didn't turn out to be a differentiable one, but still everywhere of this example you will find a subgradient. And also here, so if you think about this absolute value function, then also here you will find the subgradients easily. So okay, that's a nice property to have. And if we have it, then the idea is just that now we do everything we did before. You just do all your gradient descent variants that we like so much. So we just apply them, but with subgradients instead. That's the idea. And even the theory, same can be said there. Most theory we have for gradients can also be translated and to be true for subgradients. Sometimes convergence is a little bit slower, but similarly, these objects can be used very similarly. So okay, and then what we said, then we discussed a bit here, like we said here, there was only one subgradient here, right? So at this point here, you only have G equal the gradient. Of course, it's always, if you have gradients, then you can always do this. And then you know the gradient does have this property if you're convex. So then that's what's written here. If you're convex, then the only subgradient you can have is actually the gradient. So then you're back to the old story. There's nothing new here. Just saying this as a special case. So it's kind of a generalization of what we had before, right? Okay. And then here is what we already said. So whenever you did gradient descent before, just to keep doing the same thing, do it now with one of the subgradients you have at where you are. You might have several, right? Then you just pick any of them. So pick a subgradient instead of a gradient. So, and then do the same thing. And yeah, this is really kind of is worth mentioning in machine learning, because it often makes sense, or even in many deep learning applications, we have things like some activation functions that we use. So this will come in the second part of the course. Like this function here is like the ReLU activation function, rectified linear unit of this function, and it's also known as the hinge loss. So these are a function which are often used in machine learning, and they all have this property that most points they are differentiable, but then they have usually one point where they're not differentiable. So here is the absolute value function. These are two examples where we surely need some methods like this. Okay, so now we just broadened our toolbox. Now we can also tackle these functions whenever we have a way to find these guys, these subgradients. So that's not always a trivial endeavor, and it's not. I cannot give you one recipe to always find a subgradient. It really depends on what kind of function you have, if it's easy to do or not. And so, but one thing I can give you to help a little bit with subgradients is the chain rule. So let's actually start with that. So is there, I mean, you're all familiar with the chain rule for usual gradients. What you can ask is there a similar thing for subgradients? And that's something I'd like to give you. And actually you saw that this was also on the exercise sheet today. So you can use this. I just want to explain briefly what it is. So it's of course for functions which are a composition of two functions as usual. So that's what you try to analyze. So what if my function is composed of two functions, h and the inner function q? For example, for machine learning, mostly, for example, q will be the model, right, making the prediction, and then h will be the cost function. So this is what we always have in machine learning applications. So any composition, but what we want to do here is that we want that g is actually differentiable, but h is not. So now let's say we understand the h and g, and the question, of course, is can we get a subgradient of the composed thing, which consists of the two things together. And so yeah, what would you do? So okay, I have a bit of a notation mess here. Sorry, the inner function is called q, not g. So okay, I understand h and q. Question: can I now build a subgradient of the joint function L? So I want to find subgradient of L at my current position W. How do I do this? And what you do is you would again like to take a gradient of the outer function at the inner function times the gradient of the inner function. So now I was a bit sloppy what I said, but what I wrote is correct. So what we have here is that, well, we might not have a gradient of the outer one, right? So we need to use subgradients of h, and there might be several. And what this object here is just so there might be several, and this thing here. So what does this mean? H, sorry. This is the set of subgradients at of h. So that's what we write with this notation. So this thing might contain several vectors, right? Sometimes it has only one vector, fine. Sometimes it has several. And if it has several, then what you can do is you can pick any of those. So that's what it means here. I don't write equal, right? I have to pick one, right? I have to pick one of the subgradients, my outer function. And then I multiply this with the one single gradient I have for my inner function, and I'm done. That's my chain rule. The interesting thing is here is a whole set that you do have several choices, and all of them give you a valid subgradient of the combined function. And yeah, this is also on your sheet too. So this is one tool you can have if you want to compute subgradients. And yeah, let's apply it a bit so we can see that, or we can already guess that it's going to be quite useful for machine learning. For example, here it's quite clear. If I want to have mean absolute error, then I'm exactly in such a situation, right? Here I have my model, whatever it is, and then I take the absolute value of the prediction minus the truth. So that's what mean absolute error was. You can see it's not differentiable. So here the outer function would be this absolute value function, and that's exactly what you have on the exercise sheet today. So this is one example where you can apply this chain rule if only you knew what is a subgradient of the absolute value function. So this is kind of a remaining problem we haven't solved. So let's have a look at that, and that's actually here. So can you tell me what is the subgradient of this thing? So so it's a number then, and so a real number, right? And I have sorry, so yeah, I have to do a bit of a case distinction, right? So if, okay, where is the, let's have a picture. Here's my absolute value function. And here is E in this sense. So if I'm in this region, then there's nothing to do, right? So everything is nicely differentiable. So that's here and here and here, no problem. So that's why, like, when we are on the left side of 0, we are good. When E is less than 0, then of course it's just a slope -1. So it's a very simple function. And it's differentiable everywhere, strictly left of 0. Same thing right of 0. Then the slope is +1, before it was -1. Now, yeah, what's here? What's the special case in the middle? Which numbers are allowed to be subgradients? Or can you give me one number which is a subgradient at 0? So if E is 0, what do you think? I heard 0, which is a valid answer, yes. And I heard another answer that any number between -1 and 1, and that's both correct, yes. Because here, yeah, here's -1, here's +1, here's 0, here's something in between. So all these are allowed. So anything between -1 included and 1 included, that's all fine. These are all subgradients. So here you have infinitely many choices, and then here you have no choice. And of course you can do a similar argument for the ReLU here. Here the subgradient will be everything between 0 and 1, and yeah, it's really the same argument. For easy functions like this, we can just manually see what are all these linear functions which are below it. So we can explicitly write it down. So we have found all subgradients of this very easy function, right? And well, this is not the general recipe, right? This is just for this case, for absolute value. For other functions, use the chain rule. That's the recipe. And does that make sense? Yeah. You're saying the 0, 1 here is a useless subgradient if you use it for gradient descent. Exactly. It's kind of true, yes, because you're right, because then I don't move anymore. If my gradient or subgradient, whatever, is 0, I don't move. So I'm stuck. But it's actually, we will get back to this in a second. We say it's actually also an interesting observation, because you say, if you have gotten somewhere where the gradient is flat, then you're actually in a very good place. Then, because what that means is that there's no way to improve. So you will actually be at the optimum if you're in a convex function, for example. So it's actually interesting to look at these guys, gradients or subgradients, and see what they are. And interestingly, is some of them better than the other? Is it really a bad one to pick the 0, 1, or should you pick the -1, 1? It's not clear, right? Because you're already at the optimum. So actually, it would be kind of stupid to move away from the optimum. It's actually, but in theory, this is actually also a kind of open research question. Nobody knows which of the subgradients is a better one. So the theory just tells us pick any one of them. Any one of them is fine. Make sure you have a good step size, and then things gonna be okay. But if you're at a particular point and you have many choices, we don't know which one is a good one. But it's very interesting if 0 is one of your choices, then that tells you something. It doesn't tell you where to go, but it tells you that you're actually at a good place already. So I'll come back to this a bit. Thanks for the comment. Any other questions? Cool. So this is maybe a bit scary for those who haven't seen subdifferential subgradients. This is called a subdifferential, but it doesn't matter. It's just a name for this set of all candidates. Okay, so what do we do with this? And again, same as before. There's nothing you need to learn except that you need to believe that whenever you did SGD before, now you can do the same thing with subgradients. So when can we do SGD? Well, that's when we have a sum structure, which is always in machine learning. And now what if these guys are potentially not differentiable? And then the answer is basically what you said. You just still run SGD, but you just use a subgradient of whichever end that you're currently working with. So as you would expect, so you can be happy and you don't need to change anything. You can just use the usual algorithms we have. So some people are not even honestly saying what they mean when they say SGD, because in most deep learning cases, they actually do mean stochastic subgradient descent. That would be the correct name, but people don't mind calling it this. And my back button is broken. That's unfortunate. Okay. Okay. We have a small exercise here. And that is to again take linear models with absolute value. So actually what we had before, what we discussed, how to compute the subgradient. And what's different here is that, okay, again, you have seen linear models with GD, and now we have seen linear models with SGD. So now, yeah, do this one for SGD. See what the update would look like for SGD on the absolute value, right? This is exactly what he. Wow, my iPad is dying. Oh wow. Interesting. Sorry. Maybe it's time for. Well, give me 1 second. So. Okay, now it's killed itself. So. Oh, okay. We're kind of back. So the summary here was, yeah, just run it anyway. Pretend you didn't see the problem of non-differentiable. You just run it anyway, but use a subgradient whenever it's needed. That's the idea. Subgradient to the ln. And again, I mentioned the exercise. So for linear models, that actually is in the lab one. You saw it, right? You can code it, and then you can also on paper figure out what this stochastic subgradient would be. And before the break, I'll just give you a super small recap of the landscape on how expensive they are and what they can be applied to. So we have gradient descent, and we have SGD. So right in gradient descent, we use L, and here we use Ln. And then I want to summarize that like we have smooth, which means differentiable, and then we have non-smooth. L. So for example, mean squared error was smooth. So we did have gradients, and then mean absolute error leads to non-smooth optimization, almost no matter which model you use, but just the loss already is non-smooth. Therefore, the whole thing will be non-smooth. And then what are the objects I use? So here I use the gradient. So now, if you're non-smooth, then you can still look at the whole function. Then you use the subgradient. Again, I write this. This is the set of subgradients. So you pick one of them and you use that. If we have SGD, then it means we are working on a sum structure and we only use one element of the sum. Then we use only the Ln to do our step. Ln. And then if you have both this sum structure, and we have non-differentiable points, then we use one of the subgradients of Ln, as you would expect. And that's the whole summary, Ln. And I also give you the complexity. We already did it, right? Just a recap. So it was n times d as a cost for linear models. Same can be said if you use mean absolute error. And then we have SGD, which is much cheaper, n times cheaper. So we only spend cost d per step, right? I'm not telling you how many steps you need, just telling you the cost of one step. So okay, I think that's a good point to take a break. After the break, we'll look at constrained optimization for a second. See you in 15 minutes. Okay, let's get started again. So the next part will be a little bit shorter than the previous one. And without the mask, it's better. Okay, so yeah, I get that this is also a bit tricky with the chain rule, and it's actually really nice that you spend a bit of time on the exercise as well. And I really encourage you to combine these two things, right? To see, okay, now I have linear model W. It's really easy in the linear model case, right? And you have the prediction is just X times W. And obviously that's easy to differentiate, right? And it's differentiable everywhere. And then that's your inner function, the Q. And then you have the outer function, the absolute value. And that's really nice to play around with this if you get the correct result, which means you have to do a case distinction depending what the inner value is, right? Because E will take the role of Q. Depending on this, the outer value will take this. That's the subgradient of H, right? That's where you have to either U-1 or U1 or something in between. Then, so that's fun too, depending what kind of fun definition we have to play with this and understand that we can also get sub-differentials. And to be honest, in deep learning applications, we said, I mean, we also have this, right? But there, to be honest, people mostly ignore this issue. They just don't bother to say if there's no gradient at all. So they will just if you do automatic differentiation in PyTorch or so on, then this is actually not treated, right? It's just it's just pretending that either it will take the gradient just coming from the right, where this gradient still exists, or it will take the limit from the right, but it's not aware that there actually exist non-differentiable points. So PyTorch will not do this. But if you want to be sure things work, then you would have to do this and we do it because it's nice conceptually as well to understand on paper that there might be several solutions, right? So, and then also, yeah, what else about this? It's also interesting to ask, when do these things exist, right? They not always do exist. So if you're differentiable, you always have a gradient, right? So that's a very clear story. So if gradient exists, then here it is, we can use it. So, and most of the functions are differentiable everywhere, right? These are just exceptions here when we don't have it. So, but then subgradients do not always exist. So that's also kind of a brain teaser, which I can give you. So, I mean, maybe you have a sine function. This function has gradients everywhere. So this gradient here, anywhere you want, you have a gradient of the sine. You've seen it, right? But does this function have a subgradient everywhere, or does it have a subgradient at some place? I mean, here, yes. Well, now I just do it over this interval, but here actually no. There's no subgradient because this is not allowed, right? You cannot have a linear function that is below the true function, right? That's what it would mean. That's what it would mean to have a subgradient, right? And it does not exist if you ask at this point W here. So this is just a toy example that subgradients sometimes exist, sometimes not. So that's a bit funny, and it also has to do with convexity. If you're actually convex, then it's fine. Then they always exist. So sorry, that might be a bit surprising, but it's fun to think about. So, is there another question on this? Maybe there was a question for the chain rule, or is it more or less clear? Okay. Then the next part is a bit easier, I would say, where we just say, okay, there's one or two more things we should care in optimization. One has to do with what you asked in the beginning, that what if like 0 is a gradient? Does it give us some good information about are we at the optimal place? And then the other thing is, what if we have constraints, which we must additionally respect? So, and that's what we want to do first. So far we don't need on this part, right? But what if there is constraints coming into play, which might be physical constraints, right? If you have a robot, then and these are optimizing over the body positions of the robot, then you must have a constraint that the arm is attached to the body somewhere. So that's one possibility where constraints can come in. So you have some equality constraints or inequality constraints on your parameters, or they just want to be in a particular set C. That's also maybe the most general way to write it, just to write, yeah, my parameters must always remain in the set C. If you look at it, just look at the right picture here. It just, so this here is my space of W's, 2 dimensions, and this, maybe I have a set of this shape, which tells me I always must remain in this set. And if you think about it, how would this look like when you also plot the function value? Then that's what we have here on when we have the vertical axis showing the function value, then you have the same thing. What you're trying to do is finding the lowest point in W, L, the lowest point of the function L, which is here. And you hope that point is also in the set. right? So that's, and if not, you just ask about what is the best value I can get while remaining in the set. Okay, yeah, nothing happened, just a definition. So, but how to solve this? And this, there's maybe 2 or 3 methods, and again, it's not a super generic recipe. Maybe it's a bit about, so one is the second one is a bit soft. It's kind of saying that, okay, if you have a constraint problem, you should convert it into an unconstrained one, and that's actually a good advice. But there's of course several ways how to do it, right? So, and that's what we could want to say a little bit later. But first, we want to talk about the classic method for it, and that's like, just, can I still run gradient descent? That's always what you should ask, because gradient descent works so well. We understand it. So, can we still run gradient descent when we have constraints? And the answer is, it's not completely obvious, right? And here is why, right? So, because when you're currently at your current point and you go to a gradient step, here's your gradient step. The problem is that your new point, so maybe this is WT, then you go to a new point, WT plus 1, right? The problem is that point might be outside the set. So, because we have no control of if we're close to the boundary, if our step size is large or small. So it can happen, right? It can happen that you end up outside the set, and this is not allowed. So you must do something to correct this fact. And the easiest thing to do is to actually use a projection to go back to the set. So after every step you have done, you do this green thing, which is the projection. You say, I wanted to go here, but I cannot. So I go to the point called projection of this candidate. And that projection is defined to be the closest point to where you want to be, but in the set. So that's what a projection is. Here is the definition. Projection onto a set. Actually, I mean, for any set, it's defined like this: just the closest point to this point where you want to be, right? But V must be in the set. So that's the projection. The V which is closest while respecting the constraint. And you can do this for all kinds of sets, and that's exactly what we have here again. So here is where we wanted to go, and then here is where we actually go. Okay, what can we say about projections? So sometimes these projections are easy to compute. It really depends a bit on the geometry of the set. What is also one small interesting property is that if you have a set which is convex, then the projection actually is unique. Maybe that might be convenient. It's not necessarily a problem if it's not unique. I mean, you can maybe imagine an example like this, and if you're currently here, you ask, what's the projection of my point onto the set? And then here you kind of have 2 candidates, so which might be. It looks to me, I'm not good at drawing, but it looks to me that these 2 candidates are equally close, and these seem to be the closest points to the set C. I mean, in the set C, closest to W. So, I mean, this set is not a convex set, so just to give you an example, that sometimes you have several projections, several candidates which are closest. And however, if you happen to have a convex set, then there's only one closest one, and then here is a potato, which is a convex. So, and then have no matter where you start from, you will be, there is only a unique closest point. So okay, and for those who don't remember, the definition of a convex set is very easy. I think you have seen this. It's a set is convex if between any 2 points, the line between them is also in the set. So here's the line between 2 points. It's in the set, so that's nice. And here, not nice. And also, this is a bit an artificial example here. It's just saying that if the set here is defined that the boundary here is not included, then you also have that. That now I found a line segment which happens to be not in my set, so that means the entire set does not have the convexity property. Okay. Any questions on this? This is just to give the definition and then to say that it can be useful for projection. It's not the only thing which matters, but it gives you one property. And also, I think you probably heard this before, that you know that if you take intersections of two convex sets, then they're convex. That can be sometimes useful. So, because sometimes you might have more than one constraint you want to satisfy. Maybe you have one constraint you need to be in this set, and another constraint you also need to be in that other set. So you have kind of the intersection of the two being your constraint. So that's also one tool which can be useful sometimes. Anyway, you can use a projection onto any set if you are able to compute it. I mean, it's just a definition for us. And then, so yeah, we have defined what projected gradient descent is. So that's the update rule here. And it's really just a classical one. But after every step, you do this projection, right? So this is the new element. We do the classical step, which is inside here. And then we do the projection afterward. So. And then, so this is where you go. So this is actually your WT+1. And then what's next? Then again, you do the next step. So then you again want to go to some candidate, but you're not allowed. So then you again project back. And then maybe next time, maybe the gradient brings you here. So now you happen to be inside. This, of course, can also happen, but that's good. So now the projection, what does the projection do if I happen to be inside? And now, so I'm here. So what is the projection of this onto the set? If my W is already inside. It's W itself, thank you. Exactly, so it does nothing. So you just check, yes, my constraint is already satisfied, therefore I don't need to do anything here. I can just keep myself as the next iterate. And then, yeah, you just go on and on. So this again is the iterative algorithm. So you repeat, of course, because gradient descent, you need to do many, many steps. And then at the end of today, we will talk briefly about, yeah, when do we stop? So that's another a bit tricky question. It's a bit more tricky even when you have constraints. So it's easier to discuss in the unconstrained case. Okay, I think that's all I wanted to say about the projected gradient descent, except I just want to say that the cost is not so trivial. So the cost now has two components. So of course, the cost of the inner part we already discussed, like just the computer gradient. Now there is an additional element, which is the projection I have to do as well after every step. So that, of course, can also be costly. And then how much this projection costs is also something that depends really a lot on the geometry of the set. Some sets are easy. For example, on a Euclidean norm ball, it's super easy to find the projection. Some other norms can be very hard. So on L1 norm for those of you who know, so that's the sum of absolute values. On the L1 norm, people can find the projection, but that's actually quite a non-trivial algorithm. And then some other LP norms. Actually, I think nobody knows how to compute the projection onto that exactly. And or onto a cube, it's again easy. You basically just cut all the values which are too high if your constraint set is a cube. And yes, but the good thing is that it's actually quite rare in machine learning that we need to respect this so-called hard constraints. So it's actually much more convenient practically to treat this as soft constraints, which means you solve just a kind of a different unconstrained problem, and that's something that we want to discuss now as a kind of a second approach. So right, so we mentioned these two things. So either we do project gradient descent or we try to transform it into an unconstrained problem. Is there any question still for the projected gradient? If not, then let's look at this part B. So can I, if I just have my problem, it has constraints, so can I transform it into an unconstrained one? And yeah, it's not going to be exactly the same, but yes, this is something that is also a possibility. And the idea is really to just modify. So before you just had the constraint problem. So constraint is here, right? And that you don't like, so you kind of try to find some interesting way to instead solve what we call a penalized problem. So which has no constraint on W, but some kind of penalty function W here, which you add, which tells you that if you're actually outside the set, you have to pay, right? And how much you pay, that's a bit up to you as designer of this alternative variant. So that's the idea. And so that's what we call these kind of penalty functions, and there, right? This is an example. Then this one we will also briefly discuss. And so this is the idea of this penalty function. So the first one I want to discuss is just this is a bit of theoretical interest only. So this is saying, okay, just yeah, you can define this function here. If you're outside the set, then you must pay infinity. When you're inside, you must pay nothing. So this is called the indicator function. So again, like, I mean, this is the original objective. And then this is the additional penalty. Okay, so I mean, this is nice, and actually, this problem is completely equivalent to the constraint problem we have, right? Because it's you can check, right? It's really identical. It means the same thing. It just means that you must stay inside C, otherwise you pay infinity, which means it's just not allowed to be outside. The question is just with which kind of algorithms could we solve this? So because yeah, this might be a bit hard to solve. So the indicator function is actually still, yeah, it's still if your set is convex, then this is a convex function. Well, that's just one interesting information, but it doesn't really mean that it's super easy to solve. So because if you're outside, there's just nothing you can do. There's no, your function is not even defined. You cannot compute the gradient. You cannot really find a subgradient either. So we do not have reasonable algorithms to solve this, except you go actually back to just to projected. That's the only maybe reasonable thing to solve this. So, and where this problem comes from, the infinity makes that makes it a bit harder to. It doesn't work to use this in our gradient-based algorithms, right? So that's why it's a bit a theoretical approach, not so useful. Let's take something a bit more useful. So, and that is now the real idea of this penalty function is really to have a finite amount of cost you need to pay, this extra cost. So if you're in the set, you pay 0. And if you're outside, then you have to pay maybe depending on the distance or some distance measure from how far outside you are. So here, this is too drastic, right? But here is an example where this makes a bit more sense. And the example is for the constraint set being a linear equation constraint, which of course is a very reasonable set of constraints to have. You can just say, okay, yeah, maybe someone told me that I need to have a linear constraint on my W. It happens, is really common, right? You have all this kind of linear programming for those who have seen it, and this can really often make sense. And then, so what can I do? So what I'm telling you is that here there's one very easy measure to measure how far away are you from satisfying this. And of course, it's natural to use the norm, right? So norm is just one way to measure how far you're away, right? If you satisfy the constraint, this is 0. If you don't satisfy it, then this norm is kind of telling me a bit like, how bad is it? How far away are you from being inside set C? And yeah, but it looks a bit trivial, and it is, but still this is a very good approach because this is a nice function to optimize. Norms have really nice properties. Gradient descent will work really fast on this part. It's very easy to compute gradients on it. So this is all super nice. And this is what it is anyway. That's our original objective. But now we have no constraints anymore. So now we can suddenly apply our well-developed arguments for the unconstrained case, right? And that's really what everyone does in deep learning as well, right? If you have a neural network do something, but you would like it to do it a bit more like that, to have the arm joint of the robot a bit more realistic or so, then you would always do it like this, right? Because then you can keep using your unconstrained optimizers, and you just make a large lambda value if you want the system to respect your constraint a bit better, right? It's not going to respect your constraint perfectly. It's not going to give you 0 here, right? But it's going to give you a small value if you make a large lambda, and if you then optimize the joint problem well enough, right? So you can put this lambda value, which is this trade-off parameter. So you can put that to balance the two objectives. So how much do you care about the original objective, and how much do you care about the constraint being closely satisfied? So does this make sense? We have a question in the chat. Okay, so the question is, if you have a set C, then how could I construct a matrix A which would describe my set C? And that's a very good question. Thanks, people on Zoom, by the way. So, but this is not always possible. So this is you can that your set is described by linear constraints. That is only true for sets which are actually they're called polytopes, right? That's those sets which you use in linear programming. So the sets which are defined by linear constraints, they are these polytopes. They also convex hull of a bunch of points, and those we can describe like with the A matrix. But there are many other sets which cannot be described with the A matrix easily. So, for example, a circle. So I cannot describe the circle with a bunch of linear constraints. You can, but not with a finite number of linear constraints. So then your matrix A would become gigantic. So it's not always possible. So what I'm saying here is actually only that if your customer actually already gave you this A matrix, then this is what you should do. So I do not have a recipe to construct an A matrix for any set. But just to give you the intuition again, the linear system is just this, right? So it's just saying linear combination of your W's must be this number B. And that's what's written in this row here, right? So for example, you want your weights to sum up to 1. That's something which you often have. And you want your weights to be non-negative. That's the kind of constraint we often see coming up in practice. And then you can do this, and you often by hand you can find some reasonable linear constraint set sometimes. And sometimes you cannot, and this doesn't have to be linear. Maybe you have other ways to describe when you are not happy. So, and that you can use as your distance function. It doesn't have to be a norm, and it doesn't have to be a linear matrix. It's just an example, right, on how to penalize something when it's not satisfied. So, any other question? Okay, and then finally, this one is very similar. So maybe some of you have seen this. That if you have this is also if you have constraints, and what some people do is you introduce additional variables, and then you multiply this variable with how much your constraint is violated. That's this Lagrangian approach, which then tells you, okay, now suddenly I have much more weights than I used to originally have. And this one is not used so much in machine learning. We prefer this kind of approach where we have a penalty function which is non-negative, and we keep the parameters we have. We don't introduce additional parameters if not necessary. I mean, you can, it's okay, but this is maybe a bit easier. So, okay, this is just a few examples how to deal with constraints to transform them into a penalized problem. So there's a follow-up question on Zoom. So are there algorithms which can approximate any constraint set? I'm not sure what you mean by approximate. So maybe to approximate it with linear constraints. So I don't know actually. So I think it's a hard problem to or to even measure how close they are. And so here we don't want to go too much into the geometry of the sets, because in machine learning more of the problem complexity is encoded in this cost function. So there is where you have the room to make smart design choices, to choose a good model and to choose a good cost function. And they combined, that's your L. So that's what matters most. And then the other thing is just some additional benefits you might want to have on your W. Okay. So that's all for constraint. I want to finish to quickly tell you about this, when should we stop? So when we do gradient methods. So, and let's look at an example. So this is actually, I think this is maybe even more important than the thing with constraints. So maybe this is the function you're optimizing, and maybe you end up somewhere, maybe you end up here. And the interesting thing is that when you're here, the gradient is 0. So that means that you have reached a flat region. So this is your W. And that would tell you, that seems a nice reason to stop the algorithm, because you can say, maybe I'm in an optimum, right? The problem is here, we're not in a global optimum, here we're in a local optimum, but at least that's something. And often also in deep learning applications, we see that actually we do not have enough time to go all the way to a perfect local optimum or anything. So let's be honest, we will still have a gradient. We will end up somewhere here. We still have a bit of gradient. And then we see that also most of these local optima in large deep nets are actually similarly good. So that means that the picture would look a bit more like this. So that here we have two local optima, but they seem equally good, so it doesn't matter which one we go to. So that is something that can be nice, but among the theoreticians among you must be screaming when I make such fuzzy statements. So let's make a precise statement. So I want to talk about what it means to have gradient 0. So, and what I will say is that if you have gradient 0 and your function also happen to be convex, so, and the gradient is 0, right? Then what does that mean? So this is what's called the first order optimality condition. So you have found a W. So of course, what I mean here is that the gradient is 0 where you currently are at W, right? Here you found a point where the gradient is 0. So you were lucky because this means you are at the optimum. So optimality means that the function value you have there cannot be a better one anywhere. So globally, so the W you have is the best. So this, what this is called, this is the first order optimality condition. It's very strong and super nice, right? The problem is it only holds if function is convex. So that's called the first order optimality condition. If you find such a point, and what that tells you is that the norm of the gradient is actually an important measure. So, and that's what we briefly discussed before. We said, okay, what if you find a subgradient which is 0? That's very nice. So what I'm saying here is that if you manage to go somewhere where your gradient norm becomes small, then that's a good thing. That's actually how we measure optimization progress if we know nothing about the function. So if we are in a difficult landscape, there's might be many local minima and so on. So there's not much we can do, right? Especially in deep learning. So what we do then is we just look at this. We look at the full gradient and we say that, okay, if that's, at least that will tell us if we manage to go to a situation like this. So, and then that means you are either at the local optimum or at the global optimum. I mean, yeah, if you're in such a bowl. So for example, if your function looks like this, then no luck. So you will be really unlucky, right? I mean, we're minimizing, right? So you'll be very unlucky if you end up there, but there you would also stop. You would be stuck at this very high value, which would be bad. So because this can be bad, there is a simpler version of it, and that's the second order optimality condition. And what that is saying, if you manage to go here, and then if you manage to check that the second derivative of where you are is curved to the upper side, so that what this means to be positive semi-definite, then that means you are actually in a local minimum. So that means you're not in this case here, right? Because here the curvature will be negative. So that means we are not here, but it means we are like something like this here, which is good. So that's what the second order optimality condition means. So you have kind of two conditions now, first order optimality and second order. Second order is a bit less practical because in deep learning, we cannot afford to compute the second derivative. It's way too expensive because it's too big even to store. So there's so many variables, and then the second derivative is the Hessian. It has n squared entries, so way too much. So we prefer to work with first order information. And that's all for this part. And then about the step size selection, I cannot say so much. So it's just that this we have already seen that step size is a fragile thing to choose when we do gradient methods. So we saw this already, that if it's too big, the method will diverge. If it's too slow, the conversions can be very, very slow. So that is something which is difficult to tune, and that's something that we spend time also practically when we implement these methods, and something you can play with in the current lab this week. And that's it for today, and see you next week then.